Okay, this is the last video for the Packet 3 dealing with derivative connections, which really isn't new. It's just kind of reiterating and emphasizing the fun chart and then the different connections between your f prime, and f double prime. Okay, so let's do the fun chart first, and then we're going to answer these questions on this page. This is a very important page, so really I would certainly, if you can, print this page from the notes packet and then fill it out, or just do it on a separate sheet of paper. Right, pause the video if you need to copy down this diagram. But this is a hugely important conceptual page for us that's going to come up quite a bit this year. Let's redo the fun chart really quickly. If your first derivative is positive, that means f has a positive slope. It means f is increasing. If your first derivative is negative, that means f has a negative slope. That means f is decreasing. So that first derivative tells me whether the original function is increasing or decreasing. We consider that the behavior. Right now, if your second derivative is positive, that means the first derivative has a positive slope. So your first derivative is increasing. That means the slopes for your original function, f, those slopes are getting bigger, which creates the upwards curvature, which we call concave up. So second derivative positive, it's the same thing as saying the first derivative is increasing. It's the same thing as saying your original function is concave up. And if your second derivative is negative, that means the slope of f prime is negative, aka f prime is decreasing, which means your slopes for your original function are getting smaller, downwards curvature. So remember, your f prime, that's your slope of your original function, and then your f double prime, that's your slope of f prime. So those two are the same, those are the same. And then you have that fun chart, which is a very nice conceptual diagram organizer that helps kind of tie these things together. Now here we go. We've got the graph of f prime. Always pay attention to what the graph is labeled as. Sometimes you'll have the graph of f. That's rare, but you may have it every once in a while. Sometimes you may have the graph of the second derivative. That's rare, but it may happen every once in a while. Most of the time, they're going to give you the graph of the first derivative, because from that function, we can pretty much tell anything you want, both about the original and about the second derivative. So that first derivative graph, let's see, based on this graph, if we can answer all these questions about the original function. It says the domain is just -3 to 3, so there's no arrows. It's just going to start and stop. If there was arrows, cool. We would have infinities and negative infinities. That doesn't really affect a whole lot. But we'll just put them as open dots because it says the domain is restricted. Okay. Here we go. For what value, so again, it gives me the graph of f prime. For what values of x is the graph increasing? We're going to do extra. It asks for increasing. We're going to do decreasing as well. So for what values of x is f increasing? Here we go. And of course, always do your justifications, right? All these points just say justify. So make sure you do your justifications. F is going to be increasing. I always like to do the justifications first when f prime is positive. Okay. This is the graph of f prime. Positive means greater than 0. So I just need to look at when this graph is above the x-axis. So that's going to be -3. You could put a bracket there, but it's just strictly in between the two. But -3 to -2, that section's above, so it's positive. And then this section's above 0 to 2, and then this section is above 2 to 3. So if you want f to be increasing, it is not going to be from here to here, because this is not the graph of f, right? That's the graph of f prime. And if you want f to be increasing, without even seeing what the f function is, you know that f would be increasing when your derivative is positive. This is the derivative, so you just tell me where is it above the x-axis. Now, this question could have just as easily asked for decreasing. So let's do it. F would be decreasing when your first derivative is negative, aka when this graph is beneath the x-axis. So that would just be from -2 to 0. The question could have also asked, where is f constant, or where does f have horizontal tangents? F is constant / horizontal tangents. Your justification would be when the derivative is equal to 0. And then that would happen at this point, and this point. So negative 2, 0, and 2. When the derivative is 0, your x-intercepts, that's when your original function would have a 0 slope, aka is constant, aka has a horizontal tangent. Okay, so that's great. Part B, I'm going to try to scroll it, but also keep the graph on there, so I'm going to have to just gradually zoom out. Part B, for what values does the graph have a relative max? And we're going to do relative min also. So let's go for it. F has relative max when f changes from increasing to decreasing, or you could say the derivative changes from positive to negative, right? We know all that. F has a maximum when f, that same function, changes from increasing to decreasing, which means the derivative of that function, f prime, changes from positive to negative. So let's go look at this graph and let's try to identify where does this graph cross from above to below. Where does it cross from positive to negative? And I think that only happens here at the negative 2 value. So at x equals negative 2. Okay, let's do the minimum. F has relative minimum when f would change from decreasing to increasing, right? That's what it means to have a minimum. The graph was going down, then it turns and starts to go up, which means your derivative would have to change from negative to positive. So let's go try to find the value where the derivative crosses from beneath to above. And I think that's going to only happen right here, right at x equals 0. And again, if you did not want to say this or this, you don't need both, right? Either one of those two statements would be fine as your justification for your max. Any one of those two statements would be fine for your justification for your minimum. Or if you want to justify the maxes and the mins, you could kind of cut off all those, and you could say, hey, I have a max here, you have a min here, and then you could just lump all of this stuff together, and you could just say by first derivative test. The highlighted stuff, oops, it's not on the page. The highlighted stuff is what the first derivative test tells you. So if you say what the test is, you don't have to cite the test. But if you don't want to write all this, you can justify the max and the min, all of them together, by just saying these 4 words, by first derivative test. How the derivative changes dictates the type of extrema your function is going to have. Now, there was another critical point, right? Here's your horizontal tangents. Here are your critical points. That one was a max. That one was a min. Let's go look at this one. Notice how it was positive on both sides. So your function was increasing, then it was constant, then it was increasing again, right? But if the slope is positive on both sides, then that would be neither a max nor a minimum. So x equals 2, while it was a critical point, it's neither a max nor minimum, because it's an x-intercept where it doesn't cross. If it crosses from above to below, that point's a max. If it crosses from below to above, that point's a min. But if it's an x-intercept where it doesn't cross, then that would be neither a max nor a min. Okay, cool. So we've done all the stuff with the first derivative. Now let's kind of shift it over and think about, hey, the slope, right? The slope of this graph will tell you the second derivative. The slope of f prime is going to be the second derivative. So let's use that information to do stuff about concavity and points of inflection. Okay, here we go. Part C. Try to get it underneath the .cam and then get it more or less kind of straight. We're going to do concave up and concave down, right? Just so we're covered for everything. But it says, where is the graph concave down? I'm going to do concave up first. F is concave up when your second derivative is positive. That's my go-to definition. But you could also say, therefore, your first derivative, right? If your second derivative is positive, that means your first derivative is increasing, right? If your first derivative has a positive slope, then your second derivative is positive. So those two are equivalent statements. Either one is fine. And we can go look at this graph and pretty easily tell where it's increasing, right? Here's your minimum. Here's your maximum. So this graph is increasing from -1 to 1. and then also from this to this. So and from 2 to 3. So f would be concave up when f prime is increasing, because if f prime is increasing, f prime has a positive slope. And if f prime has a positive slope, that means your second derivative is positive, which we know means concave up. So you got to really follow the chain of logic. But if you want the original function to be concave up, you want the derivative graph to have a positive slope, to be increasing. Now let's do concave down. F would be concave down when the second derivative is negative. Therefore, your first derivative has negative slope, aka your first derivative is decreasing. So where this graph has a negative slope will tell you where the second derivative is negative, which means the original function is concave down. So from -3 to -1, right? This little part of the graph, it's decreasing, and then also from 1 to 2. There we go. Okay, and then the part D, for what values of x does f have a point of inflection? Here we go. F has point of inflection when f changes concavity. That's the definition of a point of inflection. When your graph changes concavity, you have an inflection point or a point of inflection, right? Those are interchangeable. Or you could say your second derivative changes sign. This is an equally good justification to this, right? They're equivalent statements. So f has a point of inflection when, and you could say f changes concavity, or you could say the second derivative changes sign, or you could say your first derivative changes slope, or it changes behavior. Because we know the slope of the behavior of the first derivative, that is your second derivative. And so we can go ahead and find these, and where your first derivative changes slope or it changes behavior, that's going to be where it has an extrema. So where your first derivative has a max or a minimum, those are the points that end up being inflection points for your original function. If you've already done the intervals of concavity, just look at when it changes, right? It was concave down, then at -1 it switched. Then at 1 it switched back, and then at 2. So I know -1, 1, and 2. I know those are the answers. If you already have the intervals of concavity, just look at when it switches from one to the next. And then if you go back and you look at this graph, here's -1, here's 1, and then here's 2. It's the minimums and the maximums of your first derivative. Those are the things that end up being points of inflection for your original function. Kind of weird, very conceptual. Hopefully it makes sense. Okay, now I have a little graphic organizer, because of course I do. That's going to help us keep all of this organized. So whenever you're looking at the graph of f prime, what is a certain feature going to correspondingly tell you about f? Okay, there's 4 things. The first thing is what we did in part A. The sign or the location, whether it's positive or negative, that's the sign, or whether it's above or below, whether you think about it like this or whether you think about it like this, the sign or the location of your first derivative, that is going to tell you the behavior of your original function, whether it's increasing or decreasing. And then the x-intercepts, that's where your first derivative is 0. That's where it's going to change sign, or that's where it changes location. And if your first derivative changes here, then that means your original function changes slope. And so those are going to be the extrema, your maximums and minimums. And notice, I'm going to put a little asterisk here, how it's an x-intercept is important. If it's an x-intercept, but it crosses from above to below, that is a maximum. If it's an x-intercept where it crosses from below to above, that would be a minimum. If it's an x-intercept, but it's positive on both sides, or it could be negative on both sides, so if it's an x-intercept where it doesn't cross, then it would be neither a max nor a minimum. But in general, if you want to know anything about the extrema for your original function, you would go and look at the x-intercepts on the graph of that first derivative. Okay, hopefully that makes sense. Next, we have the slope of the first derivative. which is the second derivative, or if you don't like the word slope, you can use behavior. But whether the first derivative is increasing or decreasing, whether that first derivative has a positive slope or a negative slope, that's going to tell you the concavity of your original function. If your first derivative has a positive slope, that means your second derivative is positive. That means f is concave up. Or if your first derivative has a negative slope, is decreasing, that means your second derivative is negative, which will mean your original function is concave down. So the slope, or the behavior of your first derivative, that tells you the intervals of the concavity for your original function. And then, hey, when f prime changes slope, or where f prime changes behavior, aka where f prime has a min or a max, those are going to be the spots where f correspondingly changes concavity. So those are your points of inflection. Okay, so there's 4 things. Pretty much whatever you want to know about the original function, you have a very specific thing on your original, on your first derivative that you need to look at. It flows very nice. I would definitely take notes on this, copy it down, memorize it. This and the fun chart that I showed you earlier, they are kind of the core conceptual basis for a lot of our Calculus 1 that we're doing this year, understanding the different relationships between these 3 functions. This, by the way, is nothing new in the fun chart. It's the same thing conceptually. It's just presented in a different format. So conceptually, this means the same thing as this. It's just a different way of writing it. I hope you recognize both, because I think they're both useful. But there you have it. Okay, now the last one we want to do is to sketch the graph. Remember, we're just going to think about all the possible combinations and then figure out which one of those shapes it's going to be. Let's do f prime. Let's write this again. These are probably also something that would be worthwhile for you to remember. That's your plus plus, that's your minus plus, that's your plus minus, and that's your minus minus. Okay, so we've done that multiple times, the 4 different shapes. Let's go back and figure out what's the combination for all these specific subintervals. And anytime either changes, you're going to have to get a new combination. Okay, so let's see. I think we can see. Let's just go look up here. Let's go look at the graph. So the first interval from -3 to -2, right? Just looking at this part. This is the first derivative graph, and this first derivative, it's above the x-axis, right? So since this little line segment is above the x-axis, that means your first derivative is positive. Now let's go think about the second derivative. Again, looking at just this little section has a negative slope. So for this interval, since the f prime has a negative slope, that means on that interval, your second derivative is negative. And if it's the plus minus category, your graph is going to look something like this. And now we're going to do the same thing for all the other intervals, -2 to -1, -1 to 0, 0 to 1, 1 to 2, and then 2 to 3. We're just going to figure out the combination between all those. This first one, whether the first symbol is a plus or a minus, that's whether the graph is above or below. And then to answer the second derivative, that's whether it has a negative slope or whether it has a positive slope. So let's go do this really quickly. I'm going to try to get it all on one screen. Sorry if it's a little fuzzy. All right, that's as far as it'll zoom out, so we'll just have to live with it. Okay, so again, that first section, it was above, so the first derivative was positive. And then this section had a negative slope, so the second derivative was negative. Wonderful. Let's look at the next one. This particular section, it's below the x-axis, and it has a negative slope. So I know in this interval, you'd have the negative case. Okay, the next interval, this little section, it's beneath the x-axis, so your first derivative is negative, but this particular line segment has a positive slope. So that's your minus plus. So that's decreasing at an increasing rate. Okay, between 0 and 1, right? Looking at this piece, it's above the x-axis, so your first derivative is positive, and this part has a positive slope. So your second derivative is positive, so it's your plus plus. Here you have above but negative slope, above but negative slope. And so that one is going to be plus minus this one. And then the last one from 2 to 3, it's above and it has a positive slope. So it's above, positive slope. So there you have it, right? You're just looking, the answer to this first one is whether it's above or below. The answer to the second one is whether it had a negative slope or whether it has a positive slope. And then once you kind of break it down and you figure out what the graph does during each subinterval, you just have to connect the different pieces of this graph together, and that's how you can get a curve sketch. Now I need a point to start with, right? So here it tells me -3, 0. So there's a good point. And then basically between all of these different values, I'm just going to draw a specific curve for each one of those intervals. That was terrible. Those aren't asymptotes. I'm just drawing that to help me see how it's going to split up. Right? So the first curve. Now, again, I don't really know. Like, your graph could go higher, or maybe your graph is lower. I don't really know exactly where this y-coordinate is going to be, but I just know this shape has to look like this. Okay, then the next interval, it's going to look like this. I don't know exactly how far down it's going to come. I'm just going to guesstimate. Like, maybe you think it comes down a little bit, or maybe you think it goes down a lot. It just has to have this shape. We don't know where the y-coordinate is, so that's a guess on our part. We're just getting the shape, right? There was your first curve. There was your second curve. Now we'll do the next one. Let's do something like this. Let's make it a little bit steeper. So that third interval, you've got a shape like this. And then the fourth interval, and then the fifth interval, and then the sixth interval. So again, like, that would be a pretty decent sketch. I don't really know where all these y-coordinates are. Like, they may be a little bit higher or they may be a little bit lower, but that's a pretty decent sketch. Again, any graph that you have ever done or will ever do, it just breaks down into little pieces, and within each piece, it's just one of these 4 shapes based on the combination of whether that first and second derivative were plus plus, plus minus, minus plus, or minus minus. So the curve sketching stuff is tricky. It's very conceptual. Hopefully it makes sense. Definitely copy this down, memorize this. It's very useful. And then definitely know the fun chart, because it's incredibly nice and important also. Okay, hopefully that makes sense. Please ask me questions if it doesn't, because this is important.